Welcome back to the classroom. My name is Mr. Wong. We're going through the second part of the lesson where we're talking about the relationship between current and voltage in the laws of Ohms. So let's have a look what it is, and let's look at what voltage is as well. So last 2 lessons ago, I think this was, we talked about what potential difference is. We said that potential difference is where you have a charge in an electric field and you move it from one end to another. The idea is very simple. Let's say with our charge X here, it has a thing what we call electric potential. So it has energy to be moved by the electric field from one end to another. The idea is if I move the charge, let's say it's positive from this end to this end here, okay, I would have used some kind of kinetic energy to move from here to here. So work has been done to move this charge from here to here. Now this, when it's here, the electric potential to this electric potential here would have decreased. There would have been a decrease in electric potential as we gain more kinetic energy to move it across. So this change in electric potential is known as potential difference or voltage, and that's given by the formula of work divided by charge. So we've talked about this formula before, but potential difference is either the change in potential divided by charge or work done divided by charge. Let's have a look at a couple of calculation questions here. We have a circuit which has done 1.5 10 to the minus 3 joules of work, and we have a charge of plus 10 microcoulombs. So that's minus 6. If we look at the potential difference, we have our work done divided by charge, so that's 1.5 10 to the minus 3 divided by 10 times minus 6. Now we're going to put a positive here because it is a positive charge, so that's the amount of potential difference we have created from A to B. The second question, again, we have microcoulombs, so if we substitute that into our equation again, that's the value we have here. So let's check our answers. So the value we get for the first question would have been 150 volts. The second one would have been 75 volts. Next question we have is to find the potential difference and also to find the current flow. So we have a distance separation of 5 millimeters, that's 10 to the minus 3 meters. 8 microcoulombs, so 10 to the minus 6 coulombs. So what's the potential difference from X to Y? So potential difference we have here, the amount of energy over the charge. The amount of energy we used to move this is 4 times 10 to the power minus 5 divided by the charge, which is 8 10 to the minus 6. So that's the potential difference we have at that point there. The next thing we have is the equivalent current flow. So current is charge divided by time. That was talked about in the previous PowerPoint slide lesson or the previous recordings. This here, it says 4.5 ms. Now this m here is actually mentioning milliseconds. So it's actually 10 to the minus 3 seconds. Okay. So what we have is positive 8 times 10 to the minus 6 divided by 4.5 10 to the minus 3, and so that's the current we have in amps. So these are the values we have. We have 5 volts, and then we have 1.78 10 to the minus 3 amps there. So make sure that's what you got as well. Next thing we want to quickly talk about is the concept of resistance. Now when it comes to resistance, there are 2 ways. There is things that follow Ohm's Law. So we call this Ohm's Law. And there are resistance where it's non-ohmic, but we'll talk about that in the next video recording. So in an electric circuit, you can imagine the battery as the thing that provides more electric potential. So the battery provides electric potential to charge carriers. In this case, it would be our electrons. Charge carriers. So they actually provide potential energy to electrons to go through a circuit. When it passes a resistor, this will actually take in some of that energy. So it takes some of that energy away. In this case, a resistor could be the form of a light bulb or an actual resistor. And what's actually happening is that kinetic energy or electric potential of the electron, that's being converted into maybe light energy, heat energy. And if we actually compare the electric potential it has here initially to the electric potential it has here in the final position, that difference is what we call voltage. So let's quickly look at the relationship between voltage and resistance and current. Alright, so using the wonderful FET simulator, links also in the comments of where to use this. So what we have is what we call Ohm's Law. So it says that voltage equals to current times resistance. Now, assuming that resistance is constant, whatever we do to the voltage, we should see the direct proportionality with current. So say if we have a decrease in voltage, you should also see a decrease in current, as you can see there. Okay, so we see a direct relationship there. What you can also see in the bottom here, that's our actual resistor. And you can see sort of these little particles here, like so. Now, the way that resistors work, it acts in a way to inhibit the flow of charge. So if I have a really high resistance, you can see I have more particles here blocking the current from moving through the circuit here. If I decrease the resistance, you can see that there is a greater amount of current now being able to go through this circuit here. Okay, because there's not much blocking it or interacting with the electric current. Now, obviously, in any electric circuit we use, the resistance tends to be constant. So the only way we can change the amount of current flowing through an electric circuit is by increasing the voltage. So the higher the voltage we have, the higher the current we will have going through this circuit here. Alright, so that kind of explains the relationship of voltage and current. What we did say again is, from what you saw in the simulation, assuming that the resistance is constant, so assuming resistance is constant, then current and voltage are directly proportional to each other. We can rewrite the formula out like so. If you actually graphed it out, if you did a bit of experiment with electric circuits, you had voltage over current. This value you have here, this gradient value, if I rearrange the equation, voltage divided by I equals our gradient, that's also equal to the resistance. So if I graph voltage divided by current, we will find the resistance of a circuit. Now there's two types of circuits. You have one, this example here, which is called the ohmic circuit. You get a nice straight line, so it's following Ohm's law. The other one we get is called non-ohmic circuits. And the difference with this one is, instead of getting a straight line, you get this sort of exponential curve going up like that. We will talk about the difference between these two in the next lesson. But just keep in mind there are two types of electric circuits. One's ohmic, which is linear, one is non-ohmic. You can also think of resistance, like we said, as the ability to inhibit the flow of electrons or any charged particles. Think of voltage as providing energy for currents to move through an electric circuit. Resistance is blocking the path of any electric current from flowing through. We will talk about this later on in Module 6 as well, but there's a concept of power loss. So we actually understand that it's actually how much electrons or charge carriers that's flowing through a circuit that causes inefficiency in an electric circuit. So if you have a really high current, you actually generate a massive power loss here as well, which makes sense because it's actually these current or these charge carriers that are interacting with parts of the resistor. So here's the formula that describes Ohm's law. We can work out that resistance is voltage divided by current. Another way you will find this, and most commonly you'll find this formula as written like this in your data sheet. So this is in there that you can use. Resistance is measured in ohms. This symbol is also known as omega. You can say it's volts divided by amps. That's fine too, but we generally use ohms for resistance, amps for current, and then voltage for potential difference. Let's do a couple of calculations, and then that will kind of conclude what we are talking about here. So resistance is, which is what we're trying to find, voltage divided by current. We know that the voltage is 6, the current is 300 milliamps. Now milliamps is 10 to the minus 3 amps, so 6 that divided by milliamps there. Whatever we get, that's the resistance that we're looking for. The next one we have is the current flowing through the resistance. So we have a current of, or if we actually substitute these numbers into our equations first, so we have a resistance of 100 divided by our that and that. So rearranging the equation, we get the following. And then we find that the resistance is 1.5 divided by 100 amps there. Okay, so that's what we get. And let's look at the exact values. So the resistance we'd have seen in our radio is 20 ohms, and the current flow we would have seen in the battery is 0.1 or 0.015 amps. Alright, that concludes the lesson. So we've talked about resistance, we've talked about current flow, we've talked about the relationship between voltage and current being directly proportional to each other. In the next lesson, what we're going to be talking about is the different elements that can affect electrical resistance, and also dive in a little bit more detail about ohmic and non-ohmic devices. I do hope you found this video useful. Always, if there's any content that you feel like you didn't quite catch up on, please just pause it and rewind. Anyhow, hopefully you enjoyed the video, and I'll see you next time.